Okay, we'll discuss the questions later. Okay, fine. Okay. So before I start with the before I start talking about neural networks, let's talk about something called non-linearity. Okay, non-linearity would mean a function is non-linear when is a function non-linear. Okay, so let's give a simple example. Let's say I have a function which I call the threshold function, and what the threshold function does is the value of y will be 1 if x is greater than or equal to 0, or otherwise it is 0, which means the graph of this function would look something like this. So you have your y-axis, your x-axis, and this is x, this is y, right? And any value above 0 is 1, and any value less than 0 is 0. Okay. This is a non-linear function, I claim, because you can see non-linearity in this scenario, in the sense this function is not even continuous, right? So, and in the generic scenario, what you can do is you can say y is equal to 1 if x is greater than or equal to some theta, or 0 its otherwise. Which means instead of 0, you are saying if the input to the function x is greater than some threshold theta, then greater than or equal to some threshold theta, then the value of y is 1, otherwise is 0. Okay, this is a very simple example of a non-linear function. Another example, and again, why am I talking about non-linear function? I will connect the dots later on. Just hold on for some time. Okay, this is just to set the trailer for the. This is a trailer for the picture that's coming up in a 15 or 20 minutes from now. So the second non-linear function is something called the sigmoid function. And people who have studied logistic regression here might know this function. This function ensures that your output is always between 0 and 1. Okay. Whatever be your input x, your output is always 0 and 1. In the sense, sigma of x, or I'm just calling sigmoid as sigma of x, x is the input, is nothing but 1 by 1 plus e to the power minus x. And the domain of this function x, I claim, is minus infinity to plus infinity. Okay. Now, if you think for a minute, okay, I am telling you that sigma of x will always lie between 0 and 1. So what I mean is sigmoid of x always lies between 0 and 1. But if the value of x lies between minus infinity to plus infinity, which is a huge value, still my sigmoid is from 0 to 1. How? Simple proof you can do. Okay. If you put the value of x as infinity to this expression, then what will be sigmoid of infinity? 1 by 1 plus e to the power minus infinity. And e to the power minus infinity is 1 by e to the power infinity. And e to the power infinity is such a huge number, 1 by that infinity is nothing but 0, right? So this is actually 1. 1 by 1 plus 0, which is 1. And if you consider the other scenario, minus infinity, then 1 by 1 plus e to the power infinity. And as I said, e to the power infinity is such a huge number again. It is 1 by infinity, and 1 by infinity is nothing but 0. So, and where would you use a sigmoid function here? Sigmoid functions are typically used in when you want to estimate the probabilities of the data. Okay. When you want to, if you have a logistic regression model where you are predicting between two classes, you can predict the value of the class y equal to k, or predict the value of y given x probability, and then you can do a threshold function to do the final calculation. So the graph looks something like this. This is your y-axis, this is your x-axis, and this is your graph. And what is this value? So this is the x-axis, this is the y-axis, and if x is 0, then y is 0.5. Now, another last nonlinear function that I will talk is something called rectified linear unit, or ReLU. ReLU stands for rectified linear unit. So what does rectified linear unit do? Your y is nothing but equal to max of 0 comma x. Okay, which means your graph would look something like this. If your x is negative, then max of 0 comma negative is 0. So all the negative values are pushed to 0, and all the positive value remain as it is. So your graph looks something like this. So this is your all negative values pushed to 0, and then it is nothing but y equal to x. This is x. This is y. Okay. Now, so these are three nonlinear functions that I talked about. Now let's start with the concept of a neural network. So a neural network is something very simple. Okay, we have learned about, you might not realize, actually you have learned neural networks for some time now. So if you remember a very popular expression in linear regression, which was y equal to w transpose x, right? This has been depicted pictorially by a neuron. How? So this, let's draw a circle. Okay, let's draw a circle. The circle contains an input x. So these are the features of the input, x1, x2, x3. So these are the different features of the input, right? And then each of them have a corresponding weight associated to it. The edges denote the weight, while the nodes denote the input. And over here, you have your y. So what this does is, it does the computation y equal to w transpose x. This is just pictorially representing what I wrote on the top. I wrote y equal to w transpose x. And how do you pictorially represent it? Is, think of this as the function which actually does the dot product of w1 x1, w1 x vector, in the sense w1 x1 plus w2 x2 plus w3 x3. That is w transpose x, right? So, and now what other thing that you can do is, you can apply a non-linearity, in the sense, okay, let's say you are trying to build a logistic regression model. Okay, you have built that model, and when you put x1, x2, x3 along with the corresponding weight w1, w2, w3, you output y equal to w transpose x, and the output is, let's say, 1000. Now your logistic regression now outputs a probability, right? 1000 cannot be a probability, right? If 1000 is a probability, then it's difficult for you to sit on the exam after 20 days if you think 1000 is a probability. 1000, your probability lies always between 0 and 1. How can you enforce that the value of w transpose x will always lie between 0 and 1? You will put something called a sigmoid function. So what we will do here is, this part of the network computes your, so I will divide this circle into two semicircles. This part computes our y, this part computes our a. So what is a? A is nothing but the sigmoid of y. And what is y? Y is nothing but your w transpose x. Okay, nothing, I have actually not taught anything till now. Just whatever we learned, I have just pictorially represented this. And this thing is called a neuron. Okay, this entire structure is called a neuron. And why is it called a neuron? Why is it called a neuron? Because as you know, like neural networks were first designed to imitate the human brain, right? So this part of the neuron is actually part of the biological neuron, and it is popularly called in biology called soma. This part is called the dendrite. No, this part is the output is called the axon, while these parts are called your dendrite. And these axons connect to other neurons. Okay, fine. Now, so if I ask you one very basic thing now, that let's say you want to learn the AND function, learn the Boolean, you want to build a model that can predict, given the value of two variables x1 and x2, what will be the value of the AND function of them, which means, so my training data will consist of, in this case, four instances. Let's say there will be two features, x1, x2, and this is my y, right? And this is like 0, 0, 0, 1, 1, 0, 1, 1. And do you know the true label for it? I think you know, because you have studied digital electronics and discrete maths. So 0, 0, 0 and 0 is 0, 0 and 1 is 0, 1 and 0 is 0, 1 and 1 is 1. Okay, this is something very basic. I'm not talking in detail about this. What is AND function? I hope you know that. Let's say I want you to train a model that can learn this AND function. Okay, you have some models in your arsenal, which is you have something called perceptron, you have something called decision tree, you have something called what else? Yeah, you have others as well. Logistic regression. You have a lot of models in your arsenal now. KNN, Naive Bayes, and all that. Let's say you want to learn this model. Okay, you want to build a new model. How will you do that? So let me also draw the graph for you. Let's say this denotes your x1, x2, and the x-axis denotes your x1. This is your value 1. Okay. Now, if I plot this graph, let's say I denote the class 0 as red and the class 1 as green. So 0 and 0 is 0, 0 and 1 is 0, 1 and 0 is also 0, while 1 and 1 is 1, and I will denote that by a value, by a green circle. Let's say you want to learn this model. Okay, let's say you want to learn this model. How will you learn? You might fit a perceptron, you might fit an SVM, support vector machine, you might fit a perceptron, and let's say your perceptron actually, because why would you want to fit a perceptron? You can see that these two classes are clearly linearly separable, right? You can draw a line that separates the two classes. In the sense, I claim that if I draw this line, okay, if I draw this line here, this line separates the two classes out perfectly. How? See, all the lines that belong to the above this green line are are greens, belong to one class, and all the points below this line belong to the other class. Okay, so this is okay. Now, what is the equation of this line? You might find the equation, but let me write that down for you. Equation is x1 plus x2 minus 1.5 is equal to 0. Okay. Now, if you plug in the value of x1 and x2 in this equation, so let me plug in the value. Let's say this function is f. Okay. And if I plug in the value of f, what will be the value for respective x1, x2? Can you find it out? You just have to plug in the value of x1 and x2. What is the value of f when x1 and x2 are both zeros? just to be sure you guys are not sleeping. What is the value of f when x1 and x2 are both zeros? Hey, come on. So this function is f x1 plus x2 minus 1.5 equal to 0. And the domain of x1 and x2 both can contain 0, right? Is the AND function not defined when x1 and x2 are both zeros? Then what will be the value of the function f? It could be anything. What will be the value of the function f? What do you think is the value? Sahil, seriously? 0 plus 0 minus 1.5 is what? Okay, now you are not sleeping. And the next one, if the value of x1 is 0, if the value of x2 is 1. Minus 0.5, correct. Next one, minus 0.5. Last one, last one. If x1 is 1, x2 is 1. 0.5. But now see, good. The value of f is some integer variable, which is something that I don't want, right? Because if I tell you if the value of x1 is 0, if the value of x2 is 0, then if you AND them, the answer is minus 1.5. Someone might ask you that, what the heck is this? So what will you do in this scenario? So if you have learned the, if you have understood about the non-linearity function in the previous slide, if I introduce the threshold function here, and if my threshold is 0, which means any value of x, in this case f, if it is greater than or equal to 0, then I output 1, and if it is less than 0, then I output 0. Then what will be the value of this one? It will be 0, right? Because it's negative minus 1.5. This will also be 0. This will also be 0. And this will be 1. Clear? Is it clear? No issues? Now the output makes sense, right? Okay. So now I will just write this pictorially. Okay. Pictorially in the sense you had your two inputs, one and x2. You had your two inputs, x1 and x2. And typically what happens in scenarios like this, like if you remember, there is something called W transpose X plus B. And to accommodate the B in the W, what we do is we add it as a new dimension, right? And my X has a new dimension 1, x1 and x2. Okay? Which means instead of learning two things, W and B, I can integrate that B inside the W as another element of the vector W, which is a weight vector. And my X has also the corresponding one. So it's the same thing. Okay. If you do the dot product, okay, let me do it. Okay. So what I'm saying is, so till now we know that my input vector X, which is an array X, input array X consists of two elements, x1 and x2. And my W actually is also a vector that contains two values, W1 and W2. We know till now. Okay. Now, if I say W transpose X plus B, so what am I doing? I am doing W transpose, which is I'm taking the transpose of W, taking the vector X plus a scalar constant B. And this is nothing but W1x1 plus W2x2 plus B. And what is this? This is nothing but the dot product, right? So what I am saying is, instead of writing it this way, just another way of writing so that you don't see two variables. Okay, I will write the W as B W1 W2 and X as 1 X1 X2. So now if I do W transpose X plus W transpose X, if I do, because I've integrated the B inside the W, it will be nothing but W1 X1 plus W2 X2 plus B, because B into 1. You are taking the dot product, right, of two vectors. So B and 1, so it will be B. The same thing, okay? So that's what I'm saying. So my input is rather not a two element vector, it is a three element vector, which is x1, x2, and a new guy comes in, which is 1. Okay, let me write this a bit down. Wait a second. Sometimes doesn't work, man. Very annoying. Okay, fine. So this is the scenario, and this is my circle, which I term as the soma. Okay, and the soma contains one part which computes your W transpose X, right? This computes our W transpose X, and the other part is your non-linearity A that finally gives you the, okay, let me not write this as Y, let me write this as F. I think there's some issue with the pen today. Okay, F. And this gives me a Y. So Y is nothing but A. Now what is A? A is a very generic term and it is called a activation function. It is called a activation function. And activation function, which means my non-linear functions that I introduced in the beginning of the lecture. It takes as input F. And what is F? F takes as input X and gives you the output W transpose X. So this is only what you were doing, right? You computed F, which is you computed W transpose X. Okay. And what you computed W transpose X, you input it to the threshold function A, and you got the value of Y. You got the corresponding value of Y. So, which means my X vector, oh, my X vector is now, I wrote 1, X1, X2. My W vector is very generic, B, W1, W2. So the weight I associate with this value 1 is 1 minus 1.5. Weight I associated with X1 is 1, X2 is 1. So what do I mean by this is, F is nothing but W transpose X. So W is minus 1.5, 1, 1, and X is 1, X1, X2. And so this is equal to, if you take the dot product, you get minus 1.5 plus X1 plus X2. This is the same as what I wrote earlier, right? Nothing has changed. I'm not even teaching you neural network. I'm just teaching on notation. But all in all, you are learning neural network only. Okay. Fine. So this is Nothing but very simple neural network for a AND function. And you might think, why the heck even I am doing this? Hold on again, okay? Things will go very interesting in 5 minutes from now on, okay? Things will go more interesting, okay? So now let's learn the OR function. We learned the AND function. Let's learn the OR function. OR function also contains two inputs, x1 and x2, and it gives an output y. And if you have actually learned your discrete maths and Boolean algebra in discrete integer electronics, then this shouldn't be very difficult for you to know, right? What is the value of y? Let's say I want to learn this function. Okay, if I input the value of x1 and x2, then it should give the corresponding value of y. Okay, so if I again draw the graph, this is my x1, this is my x2, and let's say again I denote the zeros as red class and the ones as the class 1. So only when the both value x1 and x2 is 0 is the output 0. In the other scenarios it is 1. Okay, this is the graph. Okay, now I claim that the graph that is drawn here, right, is linearly separable. You can see that, right? You can draw a line that separates out the two class. And what line you can draw? You can draw a line something like this. This line I claim separates out the two classes perfectly. You can see all the points that lie above that line belong to the green class, and all the points that lie below this line belong to the red class. And what will be the equation of this line? I be the oracle here, and I will tell you the equation is x1 plus x2 minus 0.5 is equal to 0. This is the equation of this line. Okay. And now, again, another small task for you, because if you are just want to be sure if you're not sleeping, what is the value of f for the corresponding values of x1 and x2 given this line? Can you find out and let me know? What will be the value of f when x1 and x2 are both zeros? When both are 0 and 1, when one is 1 and 0 and 1 and 1. Yeah, I'll give you 1 minute to think. Okay, so when the value of both x1 and x2 are 0, value of f is minus 0.5. Just input it on that equation. And when either is, it is 0.5. And when both are 1, it is 1.5. Right? And now if you again take the threshold activation function, you get 0, 1, 1, 1. Okay, which is same as what you learned, right? Your y. Okay. Now again, if I represent this as a neural network, this is my um, neuron, and these are the inputs. This is 1, this is x1, this is x2, right? And this out comes my y. This one is nothing but I associate the weight minus 0.5, 1, 1. This is f, this is a. And here also the same thing, y is equal to a of f, and f is nothing but w transpose x, where my w is minus 0.5. Okay, fine. Okay. Now comes the interesting part, which is learning the XOR function. So it is not as straightforward as the AND and OR. Let me tell you beforehand. There is some twist will come here. X1, X2, Y. So the truth table is nothing but this, and 0, 0, 0, 1, 1, 0. Okay? This is XOR. And if I again plot it in the graph, I get something like this. 0, 0 में it is 0, 0, 1 में it is 1, 1, 0 में it is again 1, and 1, 1 में also, oh, 1, 1 में it's 0, right? So it is 0. Red class, right? Now if you see, this class is not linearly separable, okay? Which means if I, let's say, draw this line, this seems to sometimes not work, and that is a bit annoying, but okay. Let's say if I draw this line, this line, does it separate out the red and the green classes? No, because there is a point above this line which is red. So you might argue that no, 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 no. You have been, what you can do is something like this. Then if you see again, this is also not correct, because your point above the line is classified as red. So you might say that, okay, fine, let's do it this way. So point above this line is classified as green, which is okay. But there is a point below this line, which is classified as green, which is not okay. So that is why this is also not, this is, if you look at this, there you cannot find a single line that can separate out these two classes perfectly. And this was the reason why even after perceptron was implemented in 1958, introduced in 1958, machine learning only came to power recently, because there was something called AI winter. Some history I'm giving you for something called AI winter, where someone, when a person called Frank Rosenblatt, he coined the term perceptron, saying if two classes are linearly separable, then you can actually do predictions. And people were like, wow, it's a new thing, amazing thing that has been found. And then someone came and said, hey, can't you learn the XOR function? What is this? This can't even learn a simple function like XOR. And he's correct, right? This XOR function is not linearly separable. But here is the catch. If I consider two lines, okay, which is, let's take this line, one line, and let's take this other line, okay. And if I claim that all the points that lie above this line and all the points that lie below this line are linearly separable, and all the points otherwise are not are reds, belong to the class 0. Okay. So what do I mean by this is, let's say this two lines you have learned are two hypothesis functions, h1 and h2. This is one line h1, this is another line h2, right? So this is my h1, this is my h2. And if you have understood the previous slide, then my h1 is nothing but the OR gate, right? Which means this will be nothing but 0, 1, 1, 1. And H2 is nothing but an AND gate. Hold on, because if you see the line, okay, it's an AND gate, but it is actually the opposite of it, which means it's a NAND gate. It's an AND gate, which means the class line, the point above this class should have been red, should have been green, so that it's 1, but in this case it's 0. So it's a NAND gate. It's a NOT of an AND gate. So H2 is nothing but NAND gate. So it is, if you know the NAND gate, then the output of this is 1, 1, 1, 0. And if you take as H1 and H2 again, you get the final, you get Y. Okay. So which means Y is nothing but H1 and H2, where my H1 is the OR gate x1 plus x2, and my H2 is the NAND gate x1 bar plus x2 bar. Okay. So how do I learn this? Okay. See, and OR functions were very easy to learn because they are linear classifiers. You can just draw a single line that separates out the two classes, which is something very simple. But how can you learn something like a XOR function, right? So, and this is the magic about neural networks here. Okay, please pay attention. So we have already designed a classifier for H1, right? There is already a classifier present in the previous slide for H1, which is the OR gate. Okay, and for the NAND gate, again it becomes very simple. Whatever I have for the AND gate, if I just take the negative of it, which means if I take the minus of the AND function, that is the NOT of it, and then I can get the NAND gate. So which means my neural network will now look something like this. I have my inputs, which is, this is the bias 1. I mean, this is the value 1. Okay. This is my x1. This is my x2. Okay. Let's say this this neuron learns h1. How does it learn h1? It will just say h1 of x is nothing but your OR classifier, which is x1 plus x2 minus 0.5. So I can input this and connect this with this, this with this, and this with this, and then the weight of this is minus 0.5, weight of this is 1 and 1. Okay. But also, let's say I have another neuron, H2, that learns H2. In the sense, let me use a different color. This one is connected to H2, let's say using this edge. This X1 is also connected using this edge. This X2 is also connected using this edge. The value of this is nothing but 1.5, because the value of AND was minus 1.5, if you remember. So the naught of it will be plus 1.5. This was 1 earlier, it becomes minus 1. This becomes minus 1. Okay. So this neuron H1 here computes the function, so computes the function of the OR classifier, and H2 of X will compute the function for the NAND classifier. Okay. Again, if you're not convinced with this argument, why is it a NAND classifier? Maybe draw the NAND gate truth table and plug in the values of X1 and X2 and convince yourself that actually this works. Okay, so now what do I do next? If you remember, there was one more step, right, to get Y, which is what? I have my H1, I have my H2, right? Now think of this as another input, X1 and X2. Instead of H1 and H2, these are some other inputs, X1 and X2, or X1 prime, X2 prime. What you are doing is something called the AND gate, and you already know the AND classifier. So if I connect these two inputs to another neuron, that is nothing but my AND classifier, and it gives me the value of Y. And it's an AND classifier, so I will also have my bias, and the output of this bias is minus 1.5. This is 1, this is 1, this is my F, this is my A. So what I'm doing now is, now my Y is the A of F, and my F is minus 1.5 plus H1 plus H2. Okay, and my H1 is this, the given on the top, and H2 is also given on the top. So now this is called a neural network. Why? You had your inputs, which is something that was given in the first case, 1, X1 and X2. You feed them into different neurons that output some value, and then you combine the output of those neurons to generate your final output. And this here, this thing here on the middle is called a hidden layer. Layer meaning it's a set of neurons. Okay, in this case there are two neurons in the hidden layer. Okay, and this here called your input layer. And this thing here is called your output layer. Okay, input layer, hidden layer, output layer. Okay. Now output layer, can it always be one? Can it be more than one ever? Can my output layer be more than one? Can I have more than one neuron in my output layer? Think. I will give you a small hint. This Y here, this F here, right? Or the Y here, which is activation of F, activation function applied on the F, outputs the value for a certain class, right? It outputs the value for a class K. that the probability that the activation function of f, correct, very good, Aditya. Probability that activation function applied on the value f predicts the value some value of class k. What if I have multiple classes? If I have multiple classes, each class will have its corresponding output layer. So what I mean by it is, let me draw generically. So I have my input layer, I have my hidden layer, okay? And now hidden layer can also be a set of hidden layers. It need not be only one, okay? Depends on how much you want to, how complex is your function you are trying to learn. So hidden layer, and then you have your output layer. Okay, so output layer I'm not making generic. That's the point actually. So let's say I have 3 neurons in my output layer. Okay, so this is my input layer. Now they might be connected like this, something like this, okay, to the hidden layers, and they are now connected something like this. Okay, let's say something like this. Okay, so this is my output layer. This one might output that, hey, so the probability that it belongs to class 1 is some x. This might output that the probability it belongs to class 2 is some y. This might say that the probability of class 3 might belong, the probability that the data point x belongs to class 3 is some z. And what you can do is you can take the max across these three probabilities, x, y, and z. Whichever is the maximum, you can say that that is the value. Let's say the value of x is, let's say the input layer is some class. If it's a multi-class, let me think. Um, what can be a multi-class? Okay, I'm not able to think now. Okay, fine. Okay, something very easy, right? So it contains the features of an animal, right? Features of any animal, and there could be 3 classes. Maybe you are trying to predict whether the animal is a cat, whether the animal is a dog, or whether the animal is a lion. Okay, just an example. So you input a picture. That picture you can represent it as a vector of integers, and your model says, hey, with 90% probability I can say this is a 0.9 probability it is a cat, with 0.05 probability I can say it's a dog, and another 0.05 I say it's a lion. And then you take the max of these 3 probabilities and say that, hey, it's 0.9. So 0.9 means 90% chances it is a cat, and you can output that the picture is of a cat. So that's an example, but in multi-class problems, you typically use more than one output layer. And so another concept which is very important is a theorem, okay, which is called universal approximation theorem. There can be direct 1 mark question on this, so please pay attention. Universal approximation theorem means by using a neural network, okay, with some set of hidden layers, input layers, output layers, you can learn any function given on earth. Any function you have, okay, you can universal means anything in the entire universe. Whatever functions you are there, a neural network can be used to approximate that function. Okay, so it means a neural network can be used to approximate any function. Okay, okay. Now And also one more important point, since you see that for or and I did not have a hidden layer, right? Because it's very simple. It's linearly separable, right? It's the easiest thing that you can ever do. So, but when it comes to XOR, the XOR function, you can see that since it's not linearly separable, you need to estimate two functions and then combine the output of those two functions. And that is why you would have needed a hidden layer. So let me write this down also. Since XOR is a non-linear function, right? The neural network needs a hidden layer for its approximation. Okay, fine. Okay, so there could be a question depending on this scenario that would you always use a hidden layer in a neural network? I think that was asked sometime back in one of the interviews that I had given. So it's not necessary that you will always have a. No, they had asked why. Huh, now remember. So they had asked when would you not use a hidden layer in a neural network? And I think the answer should be now. If the classes are linearly separable, then there's no point of using a neural network. Okay. Okay. So the last part that I will discuss today, okay, I really don't know how much they will ask on neural networks, but they will ask the basics only. Okay. I am not able to recall how we are calculating the weight of the bias and the input. Revise your perceptron, Aditya. Okay. So what you do is you give you a very simple algorithm. Okay. See. Um, let's say y equal to W transpose X plus B. You are saying I'm not able to figure out how we are estimating W and B. Is that correct, Aditya? Yes. Okay. No problem. See, what I tell you now, okay, is again, let me write this as W transpose X. I'm not considering the B. B is encapsulated inside W. Okay, I hope that is clear. Okay. So what you do is, let's say you initialize W with some random set of elements, 0, 1, 1. Let's say. Randomly you can initialize like 0, 1, 1. Okay. And you compute your Y. You are given an X, right? You compute W transpose X. Okay. And you get some value. And then what you do is, let's say this W transpose X is positive. In this case, it should be positive, right? Because uh, the weight vector is all positive, but depends on X also. But okay, let's say W transpose X, you get a positive value. You look at your Y. If Y is also positive, this outputs 1, Y is also 1, and you call it a day and say that it's okay. So everything is okay. Wait. Yeah, you call it a day and say everything is okay, right? If this is negative, if your W transpose X is negative and your Y is positive, or vice versa, if your W transpose X is positive, Y is negative, then that is a misclassification, which means Your model is trying to say that W transpose X should be 0 or -1. If there are two classes, -1 and +1, then W transpose X is telling you that it belongs to the class -1, but your Y is actually positive, right? So you will update your weight vector accordingly. How will you update is W is nothing but W plus some eta, which is our learning rate, uh, W transpose X. Okay. Again, revise the perceptron model. I've talked about this. Okay. How do you update the weight vector? And by updating, how does it become better? And this is how you update. When it comes to regression model, you will again compute y equal to W transpose X. You have your, let's say this is I called y hat. You will compute something called root mean squared error. So y hat minus y whole square root over. You will get some value. Okay. And then if you plot the graph of this function with respect to, it will be something like this, different W. And then you can use a hill climb algorithm or gradient descent by which you come to the local minima, which gives you the, this is your W and this is your loss given the W, right? And this will give you the, for what value of W will your loss function be minimum. Okay. Okay. Again, how to find out, again, let me tell you one more thing. Okay. Before going to the exam, okay, please learn three things for machine learning. Okay, I looked at the sample paper, so please learn these three things. They will definitely ask questions on this, my guarantee. First topic is perceptron. Second topic is naive Bayes. And third topic is linear regression, gradient descent. Okay, and linear regression also includes your bias variance trade-off. Okay, please make sure you are aware of these three topics. Again, if you face an issue, I'm also on Saturday and Sunday. We have two classes, so I can clear your doubts better. Okay, fine. So the last part that I will talk about, and then we'll move on to some questions, and that will be the end of the class, is backpropagation. Okay, some very basic I will talk about backpropagation, which is how do you learn the neural network, right? So before going to backpropagation, how would you express this XOR function that I drew, right? Let me bring that up again here. So the XOR function, how will you write in a vectorized form? Okay, how will you write the W? How will you write the X's and all that? So let me write the XOR function again. So this is my 1, this is my X1, this is my X2, this is my H1, this is my H2, this is my Y. Right, I'm just writing it as Y. It includes the F and the A. Okay, so it is connected like this, like this, like this. This is also connected like this, and like this. And this is connected to like this, like this. Then I have one which is connected like this. And out comes my Y. Okay, so for the first H1, I think it was 0.5, 1 and 1. And for this one, it was 1.5, -1 and negative for H2. And again, for this one, it was 1.5, -1 and 1. And then it gave me my. So how do you represent this in the form of a vector? Okay. So now my W1, so I have two weight vectors, right? I have actually not two, I have, okay, fine. So in total, I have three weight vectors. So in this scenario, if you look at here, right, just focus on this part, right? For H1, there are two weight vectors. So for H1, there are two weight vectors, which is 0.5, 1, 1, and the other vector is right. And what I do is I try to club them together, okay, and make a matrix. So which means if I club them together, then my W1 will look something like this: 0.5, 1, 1, 1.5, minus 1, and minus 1. Okay, so far so good, I guess. This is my W1. And my X will now be a matrix. The first element will be the first data point, which is 0, 0, and the 1 is the part of the bias. Second part is 1, 0, 1. Third part is 1, 1, 0, and fourth part is 1, 1, 1. Okay, which means, again, don't be confused, guys. What it means is this thing's right, this 0, 0, 0, 1, 1, 0, and 1, 1. I've just clubbed them and added a 1 before it and then taken a transpose of it. So this is my X matrix. Okay. Okay. And my Y is nothing but for this data point, output is 0. For this data point, the output is 1. Then output is 1, output is 0. Okay. So this is how my Y's look like. Okay. So what I do is I first compute something called W1 transpose X, which is my weight vector. I take the transpose of it. It becomes minus 0.5, 1, 1, 1.5, minus 1, minus 1. And this is my X here. So if you see, right, this is my H1, this is my H2, and I'm taking the multiplying them with the matrix capital X. So I'm taking the multiplication with each input vector. So what will be the output of this one? The output will be, so this is a 2 by 3 matrix. This is a 3 by 4 matrix. So the output will be a 2 by 4 matrix, which means first you will compute the dot product of vector minus 0.511 with 100, then with 101, 110, 111, and you will get something like this: minus 0.5, 0.5, 0.5, 1.5, right? And the next part will be 1.5, 0.5, 0.5, minus 0.5. So this is my W1 transpose X. Now since I have another layer, okay, so this forms my input for the next one, which is for this Y. Okay, so first we focused on the first part, which is taking the X's and then going to the Y. And now we will focus on the next part, which is taking that vector H that we had, and now we try to find the final value of Y. So first, how will my W2 look like? W2 is something very simple now because it's just one thing. one only, which is one vector only, which is minus 1.5, 1 and 1. Okay. Yeah. And my H vector maybe what I will do is I will take the transpose of H transpose, and then it becomes so I will just write whatever it was earlier, 0 1 1 1. Okay, I missed one step. Okay, sorry. So once this, I have to also feed it to the you know feed it to the activation function, and by feeding it to the activation function, I get something like this. 0. So all values that are negative become 0. All values that are not negative become 1. So 0. Why I'm saying non-negative, why I'm not saying positive? Because even if it is 0, it is still 1. So 1, 1, 1, 1, 1, 1, 0. So this is my H. Okay. And this part of the first vector here forms my output for H1. And the second part here forms the output of H2. Forms the output of H2. Just a minute, guys. Just a minute. I'll be back. Yeah, okay. Okay. So what I'm just saying is you put it in the activation function and then you get the value of corresponding H1 and H2. Now in the next step, what I do is I calculate the H transpose. So it becomes 0, 1, 1, 1, 1, 1, and 1, 0. Okay. And then what I add is, now if you see the network again, there is also this bias component here as well, right? Which is 1, right? The bias component or the extra component. So that also needs to be incorporated. So I'll also add that over here. Okay. So now if I calculate H transpose W2, which is 1, 0, 1, 1, 1, 1, 1, 1, 1, 1, 1, 0, H transpose W2. Okay. Then I get something like this. And now if I put it inside the activation function, I get 0, 1, 1, 0. Okay. So this is just a way of how you would represent it in the form of a matrix, right? This is just how you would represent it in the form of a matrix. So now again, now we are set for backpropagation. So again, I won't discuss much on backpropagation because that's a whole new derivation in itself. Derivation of backpropagation, if you know, then you will be a very good candidate, okay, for AI. But that won't be asked also, I'm sure. That's part of deep learning. But still, very basically, I will talk about why would you use a backpropagation algorithm, which is to learn the neural network. Okay. So initially you had your x's and you had your corresponding weight vectors w, right? And then this gave you a y. Now this neuron could be any set of set of hidden layers could be present and all. But let's consider a very simple scenario where yi hat denotes the value that is given by the function f applied on w transpose xi. So if you have an input vector xi, w transpose xi is the value of it, and function f could be any function that is, could be a non-linear function, could be just even f w transpose s, could be any function, okay? What I compute is something called the error. And the error, let me take the root mean squared, which means 1 by 2 summation across all data points 1 equal to n. What is the value of the model W transpose Xi minus what is the true label Yi squared? Okay, and I can write this as 1 by 2 summation of I equal to 1 to n. Instead of W transpose Xi, I can write this as Yi hat. Again, Yi hat is, as I said, it is a final output given by the neural network. Okay, it could contain any number of hidden layers, could be anything. It's a final output given by the neural network minus yi whole square. And now if I integrate this with respect to w, sorry, differentiate this with respect to w because I'm trying to maximize it, then what you get is something like this: I equal to 1 to n w transpose xi minus yi into xi. And why do you get this? Chain rule. So that's why I added the 1 by 2. So if you apply the chain rule, this 2 comes out. So this 2 comes out. And then W transpose Xi minus Yi differentiation with respect to W is just nothing but Xi. So this is nothing but the chain rule, right? So, and now, since you learned gradient descent in the last class, my new weight vector Wn plus 1 is nothing but, now you have the gradient computed, and then eta I equal to 1 to n, and you will update your weight vector as yi hat minus yi. Again, let me repeat. So you had your neural network, out came the y, and the y could be any nonlinear function or it could be just be w transpose xi. In this case, let's say it's w transpose xi, which means f is the identity function. The error is, what does your model neural network output, which is w transpose xi, minus what is the true value yi squared. So this is squared error loss, okay? And then you divide by 1 by 2. Again, I didn't explain, but why do you do it? So I'll just, what I'm doing is, instead of w transpose xi, write it as yi hat minus yi square. And if you differentiate it with respect to w, you get something w transpose xi minus y of xi. This simple differentiation, I hope you get it. And once you know the loss, once you know the gradient descent algorithm says your new weight vector wn plus 1 is whatever is your old weight vector wn minus the negative of the gradient, which is this, multiplied by eta. Now, what is eta? If you remember, eta is your learning rate, which means how much of it do you actually want to change the weight vector by. Okay. So this was all I wanted to talk about neural networks today. I won't end the class now. What I will do is we will solve some questions, and these questions are something very basic. What I will do is I will give you about 2 minutes for every question to solve. Please post your answers in the chat. Even if you make a guess, it's okay. And then we will discuss the solution, and then we will end the class. Okay. So Again, I forgot to give a quick glance of the syllabus. Today we looked at feed-forward neural networks, and then the last thing that remains for Saturday is agglomerative clustering algorithm. So this is your first question. Try to answer. I'll give you 2 minutes. Yeah. Okay, so the correct answer is C. Decision trees are prone to overfit. The problem is if you keep on fitting a decision tree from one point to the other, one point to the other, one point to the other, and if you keep on be on the belief that it will eventually you will make all your leaf nodes pure, which is all your leaf nodes contain only one class, then then you're also fitting the noisy data, and that means you are also doing something called overfitting. They are not robust to outliers, okay, even though factor analysis is a disadvantage, but that is something that you don't need to know. But since A is actually incorrect, which is they are not robust to outliers, because if you even if you have an outlier, right, you will still try to fit it, okay, and that is why decision trees are prone to overfit is the correct answer. Next question is identify the difficulties present for the k nearest neighbor algorithm. So one is the curse of dimensionality, which is if you increase the number of dimensions in your data, then it's not necessary that your model will output the correct value always. So that is the curse of dimensionality. Your error might not decrease if you increase the number of features in your vector, in your input vector. And the other problem is that you have to calculate the distance of a test point to all the training data points, and that is the biggest problem of k nearest neighbor. That is why option C is the correct answer. This was easy, that's why I didn't give you some time. Again, what does K stand for? K means clustering. I mean, if you have seen my lecture, it is nothing but the number of clusters. Which of these is not a supervised learning algorithm? Again, naive Bayes is a supervised learning algorithm. Linear regression is a supervised learning algorithm. Decision tree is also a supervised learning algorithm. PCA is not a supervised learning algorithm, right? PCA is used to reduce the dimensionality of the data. It is not a machine learning algorithm at all. Okay, no. So this was all about data science. Some quick questions. We'll discuss the sample paper on Sunday. That's the agenda of Sunday. This one is a question on data structures, which is also an important part. Solve this question and let me know the answer. Okay, I'll give you 2 minutes. Okay, something simple, very right. Stack. Who has read stack here? Use a stack, right? So if I take a stack, right? Whenever you see an number or an integer or an operand, you push it to the stack. So you push 6, 3, 2, 4. Now there is a operator plus. So you pop off the two elements from the stack and replace it with the plus operation or applied on them. Then it's a minus, right? Now, here's the thing, right? If you pop out these two elements, will you do 6 minus 3 or 3 minus 6? What do you do? 3 minus 6. Good. So, minus 3. And then there is a star, so you pop out these two elements and you get minus 18. Good. Okay. Okay, fine. So I think I have to discuss this much only for today. I will have to rush for somewhere. Okay. We will, if you have any questions, we can discuss it in the Saturday class. Okay. Fine. So in Saturday, we'll talk about agglomerative clustering. Okay. I will stop the recording.